Hello, my name is Jacob Field. I'm in M144 Calculus 1 with Professor Haruda, and I meet on Tuesdays and Thursdays from 12:45 to 2:25. Question 1 states, a designer is making a box with a square base and an open top. She wants to minimize the amount of material used for a tray that will have a volume of 1,200 centimeters cubed. The box is made by folding up the edges of a sheet of aluminum. She wants to find both the minimum amount of material as well as the dimensions of the box with minimum amount of material. Here are two diagrams of what our box will look like. To start, I will be labeling to show that this is our base. It's going to be, we'll call it X, and it's a square base, so therefore we know that this is going to be X, this is X, this is X, this is X. So these are all equal, and then we will have, let's call the height Y. So we know that this is Y, this is Y, this is Y, and that is this length here. So we know that all of these are equal as well. That is our Y. So we'll be using X and Y. X is going to represent the base, and Y is going to represent the height. To start, we will need to get the two functions. Our first one that we will do is our one that we're trying to minimize. This is the amount of material that we use. So this is A equals X squared plus 4xy, and we will do y x squared equals 1,200. This is our volume. So from here we will let's find what y equals. So we're going to do y equals 1,200 divided by x squared. This we are going to use to plug into this function. So area equals x squared plus 4x times 1,200 divided by x squared. This is equal to x squared plus 4,800 divided by x. From this point, we are going to take the derivative of the area. So that will be area equals 2x minus 4,800 x to the negative second. And let's set this equal to 0. So equal to 0. And then let's solve for x. So 2x equals 4,800 x to the negative second power, and this equals x cubed equals 2,400. So then we know that x equals the cube root of 2,400. If we want to go into decimal form, this is equal to 13.38659. This x value is also the optimized dimensions of the base. After finding the value of x, we will use this to plug it back into our volume function, and we're gonna solve for y for the volume function. So we're gonna do y equals 1,200 divided by cube root of 2,400 squared. This gives us y equals 6.69439295. This value is the height for the optimized dimensions of the box. For question 2, it states the graph below represents r of t, the rate at which the volume in cubic inches of a spherical balloon is changing with respect to time. For part A, it is asking when is the volume increasing and when is it decreasing. Since we know that this graph represents the rate at which the volume changes, we know that anything positive above the x-axis is going to be an increase in volume, and anything below is going to be a decrease in volume. With this information, we can come to the conclusion that from 0 to 5 seconds and from 7 to 8 seconds, the volume is going to be increasing, and from 5 to 7 seconds, the volume is decreasing. For problem B, it's asking at what time is the volume of the balloon decreasing most rapidly? This is at time equals 6 seconds, as this is the most negative point on the graph. Therefore, it is where it is decreasing at the highest rate. It is decreasing at negative, it's losing 1 inch cubed per second of pressure. Question C is asking to find the volume of the balloon at t equals 1, t equals 3, t equals 5, t equals 7, and t equals 8. So to find the volume at t equals 1, we'll be finding the area underneath the graph. So therefore, at t equals 1, it's going to be 1/2 1 times 2, and this equals 1 inch cubed. So this is one at time equals 1. It's 1 inch cubed is the volume. 1 inch cubed is the volume. So next, for time equals 3, time equals 3, we will do the same thing, but we're just going to add to it. So that means t equals 3. It's going to be that section that we just had, 1/2 1 times 2. But then we're going to add, not because that just shows the time from time 0 to 1. So now we have to add from time 1 to time 3. And this is represented by 2 and 2 because it's 2 seconds long and it increases 2 in that section. And this is going to give us, this gives us 5 inches cubed. That's what the volume is at t equals 5. At time equals t equals 5, we're going to continue this process. So it's going to be t equals 5. Oh, I already have that written actually. So it's going to be 1/2 1 times 2 plus 2 times 2. And then we're going to add from here, we're going to add from 3 to 5 seconds. So this is going to be a 1/2 2 times 2. And this is going to give us 7 inches cubed of volume. For time t equals 7, we will do the same thing again. 1/2 1 times 2 plus 2 times 2 plus 1/2 2 times 2. And here is where it gets a little bit different, because as you can see in the graph that it goes below the x-axis. So therefore we're going to do minus 1/2 2. I'm going to have to move this down actually. Hold on, let me move this down just so I'm not squeezing it. Minus 1/2 2 times 1, and this gives us 6 cubic inches of volume. For time t equals 8, we're going to add one more to this, and that's going to be plus 1/2 1 times 1, and that's to show the last from 7 seconds to 8 seconds, and that is going to give us 6.5 inches cubed. So that's going to be our values for at time equals 1, time equals 3, time equals 5, time equals 7, and time equals 8. For part D, it asks write an integral to represent the volume of the balloon at t equals 7 seconds. So to do this, we will have from 0 to 7, we will have an integral to represent the function r of t. There is your integral. For part E, it asks to find the value of the integral you wrote for part D. In other words, find the volume of the balloon at t equals 7 seconds. You can use geometry to solve this. We actually already did this in part C, and we found that at time equals t equals 7 seconds, that it was 6 inches cubed. Part F asks when is the balloon at its maximum volume, and this is at time equals 5. Part F asks when is the balloon at its maximum volume, and this can be found by looking at the graph. We can see that we know that at t equals 8 that it was only at 6.5, and we know that 5 was at 5 seconds. That's when it switched from increasing to decreasing. So therefore, we know that at time t equals 5, the balloon was at its maximum volume. I would like to thank you for listening to my explanation for question 2 and question 1 for the final long assessment video problems. My name is Jacob Field. I'm in Calculus 1 with Professor Haruta. And I meet on Tuesdays and Thursdays from 12:45 to 2:25. Thank you.